This video is about using the JMP Statistical Concept Applets. If you're using JMP Student Edition, which I have open on my Mac so you can see the menu bar along the top of the screen, under JMP Student Edition there's a menu option called Applets, and this is where these applets reside. There's also a link to the documentation for more information about the applets directly in JMP Student Edition from this link. And there's additional resources, other applets like a permutation test, and links directly to demonstrating power and p-value and a few other topics. If you're using JMP, the standard version, or JMP Pro, then your menu bar looks like my menu bar does along the top, where there isn't the applets option, and instead you can go to the help menu to this option that says sample data. Not sample data library, which is just an alphabetical list of all the sample data sets, but this last option right above renew license that says sample data. If you click on this and scroll toward the bottom on the right hand side, there's a section that says teaching resources. And under this section, there are a number of options under teaching scripts, including these interactive teaching modules, and these are the applets that we're going to look at today. So I'll open them from the JMP Student Edition from the Applets menu bar. Let's look first of all at the distribution calculator. So the distribution calculator allows you to choose from a whole bunch of different distributions, like a normal, a t, a chi-squared. If you have a t distribution, the parameter of interest would be the degrees of freedom. The higher this number gets, the closer this will start looking to the normal distribution. So I just hit enter. If I want to reset this to the default, then I click the reset button. So if I change the degrees of freedom, watch as I hit enter, you can see that the distribution is going to look a little more normal. So it got a little bit fatter compared to when the degrees of freedom is 10. If I make the degrees of freedom really tiny, like 5, this is going to be much more different than the normal distribution. So as I change degrees of freedom, I can see the distribution changing slightly. I can choose to make a calculation, so I can either input a value and get the probability out. So if I input a value, I could say, what if I look not at the 0.1, but let's say I look at 1.2 in this distribution. So the value of 1.2 standard deviations above 0. If I want to calculate the probability of being below this point, then that probability is about 85%. If I want to calculate the probability being above this point, that's about 14%. If I want to calculate the value of being between two, or the probability of being between two values, notice right now we've got a negative probability just because of rounding, because we need to find two distinct numbers. So I could say, what about if we look between 1 and 1.2? Now there's about a 0.04 probability, or a 4% chance of falling in that range. And if I want to look at the opposite two pieces, so 1 minus that, is about a 96% chance. I can do the other type of calculation where I input the probability and find the value. So if I wanted the left tail to have a probability of 75%, then that value would have to be 0.7267. If I wanted to look at a p-value of 0.05, just the left tail probability, then in this t distribution of 5 degrees of freedom, that t value would be minus 2.012. So I can look up critical values by looking at the probability that I need in that tail. If I wanted a two-sided, then that critical value changes to 2.5706 minus and plus. If I want to look at the central probability between two, where I have this most central 0.05%, or maybe a more sensible thing to look at is the most central 50%. So here's where between negative 0.7267 and positive 0.7267 is where the middle 50% lie in this distribution. So we can do this for the normal distribution as well, with the mean and standard deviation. We can do this for a number of other distributions. If I want help on this topic, I can click the Help button, and this will take me to the documentation directly for this topic. The next applet is the distribution generator. The distribution generator applet allows you to build discrete distributions. So if I have the values 0 through 10, I can input how frequently these occur, and I can build the histogram and calculate statistics. So here this is the histogram for this distribution I'm describing. Here's the quantiles for this distribution, summary statistics, and then I can look at the value, the frequency. So I already gave this information, it's repeated here. Then the cumulative frequencies, so 1 and 3 are added to give me 4, plus 5 gives me 9, plus 7 gives me 16. So this is like the CDF. So the PDF, the CDF, I can see these in proportions instead. And then I can see these contributions to the mean and contributions to the variance. Again, there's a help button if I want to see more information on how to use this applet. After these two, distribution calculator and generator, then we get into the sampling distribution applets. So if we're looking at sample means, the top section of this applet is describing the population. So characteristics of the population, for example, normal. I can show it as a curve, which is shown here, or I can use a histogram where we're randomly sampling 100,000 values to build that histogram. Because remember, the population is an infinite size, but since JMP can't sample an infinite number, we're choosing 100,000 to show this. Or I can put both. I can superimpose the curve on top of a histogram. I can change the name of this variable if I want to, so I could call this height instead of IQ. I could change the population mean and the population standard deviation. And so that will rescale everything in my distribution. I'm going to go back to a mean of 100 and a standard deviation of 15 and call it IQ, because this is a distribution that is always centered at 100 and a standard deviation of 15. That's the definition of the IQ distribution. So then the next section is about the sample. Right now we've got no sample, we've just described a population, and I should mention we don't have to just use a normal distribution. We could use a skewed right distribution, or we could use a uniform distribution to sample from, or we could use our own data. If we've got a data set open in the background, and let's go to, if I open the JMP home, I can open this last data set that I had open, big class. I'll close the home window. So I've got big class open. If I choose my data, then it asks me which of these do you want me to sample from. So if I want to sample from heights, now it'll take repeated values from the height distribution. But I'll go back to a normal distribution. I'll go back to a mean of 100, a standard deviation of 15, I'll call it IQ. And I see the summary statistics are exactly what I'm inputting over here. So now the sample characteristics, I get to choose the sample size. So I could choose sample sizes of 10 or of 20 or of 30 or of 50, whatever number I want. The default is 25. I'll start with one sample to show what happens, but I can change this number. If I want a simulation of 1,000 samples, then I type 1,000 in here. I'm going to choose to animate the illustration. This will be a lot clearer when we have more samples what this does. I'm not going to plot the normal curve on top of it, so I'll click Draw Additional Samples. So you can see for my one sample, we have a mean of just a little over 100, standard deviation of 14.97, so just below the standard deviation of 15. So this was a really spot-on sample. This is very close to the mean, the true mean and standard deviation. If I take another sample, conveniently that really illustrated my point. This one's much farther off. So 91 is the mean and 12.6 as the standard deviation. I can draw another sample, and each time I draw a sample, we're starting to build this bottom section, the distribution of the sample means. So whatever this mean value is, it gets deposited into this plot. So we had the 91 here, we had the 100 right here, and then this is our third sample here, is this in the middle, is this 95. The mean of these sample means is 95.85 right now, so just slightly above this middle sample. The standard deviation of the sample means is 4.08. So the standard deviation of sample means is the standard error of the mean. So here's the standard deviation from one sample. Here's a standard error of the mean from this distribution. And right now our n is 3. Our N in this picture is 25. We took 25 samples. We're on sample number 3, but then each time we take a sample, we drop a mean into this distribution. If I want to look at the normal quantile plot at any point, I can do that by unhiding this disclosure button here. And if I want to decrease or increase the size of the histograms so that I can fit my screen better, these buttons will help make things a little more visible on your screen to your students. So when I want to take a bunch of samples at a time, so let's say let's take 97 more samples so we can get to a total of 100. So I'll take 97 more. This is when that animate is really helpful for your students to see what's happening. When I click draw additional samples, you see each one flash before you. If I didn't click animate, I'd just see the last one. So animate allows me to see them each flash before my eyes, and I see that distribution of sample means being calculated. I can ask for more things from these little red triangles, like make into a jump data table. This is taking the data that's actually in the sample, and I could put it into a jump data table. So if I click that button, here are all the sample means from all the samples. So all the sample means, all the sample standard deviations come into a data table for me. I could then do analytics on this, so I could go to distribution, for example, and I could ask for, let's look at both of these things and just the histograms. So here's the distribution of sample means, here's the distribution of sample standard deviations. I could always restart the demo to clear everything. So maybe this time let's take draws from a skewed right distribution. We'll still use a population mean of 100, standard deviation of 15. Now it changed the variable name to count just because this is not the IQ distribution, so we're trying not to confuse you with that. Let's take samples of size 20 this time, and let's take, again, 100 samples. Let's animate this, so I'll click draw. We can watch them all being taken. We can see that each of these samples was pretty skewed, but the distribution of the sample means is beginning to become more normal. If I take another 100, I'll build that even closer and closer to a normal distribution. If we take another 100, and so on. So that's the sampling distribution of sample means applet. The sample proportion is very similar. Here we have the population described at the top, where we need to specify what the true population proportion is and give category names. So we're going to have the category name we choose and not that. So we could talk about pulling things out of a bin, and we've got blue balls and red balls. So we could have a category name blue, and then the ones that are red are just not blue. So I might be flipping a coin and I'm looking at heads and tails. So now my categories are heads and not heads. So tails is just not heads. Again, I can choose my sample size. I'm going to change it to 20. I'm going to right away take 100 samples. I'm going to animate this so we see what happens. There will be this normal quantile plot that I could look at as well. So I'll click the draw additional samples. So I'm watching each sample here, and it's actually showing me the sample proportions as we're clicking through all the samples, and then it's showing me the distribution of the sample proportions. Here's the mean of the sample proportions. So it should have been 0.2. After 100, I'm at 0.191, a standard deviation of sample proportions. So I could draw more samples and keep doing this and watch this distribution becoming more and more normal. I can create the data table from these sample proportions if I click this button right here, and I can get more help on this demo if I want to down here. Okay, the next set of applets are for confidence intervals. So for the population mean, this looks a lot like the distribution for the mean sampling distribution. We get the population characteristics at the top in this corner, and then here's the distribution of the sample data here. So let's say that this is normal, IQ with 115, sample size of 25. Let's take 100 samples right away. We get to choose, do we want to use the known population standard deviation? If we say yes, then we're looking at Z, a Z statistic for the confidence interval for the multiplier. If we choose no, then we're looking at a T multiplier. I'll choose animate illustration, and I'll click draw samples, and so we can watch them happen. And as each sample is calculated, we see the mean flash here. That confidence interval if I want to see what it is, so for sample number 100, the last one that we looked at, the actual mean is 101.926. The confidence interval on that is 94.5785 up to 109.273. So this contains 100. So that's great. This was a confidence interval that actually contained the true value. Alpha was 0.05. And then we can see the confidence intervals. So for sample 100, this last one, we can see that 100 is almost in the middle because it goes from 94 to 109. So that's this last one drawn. But each one of these little green lines is a confidence interval that captured the true mean of 100. When a line turns red, it's because it missed it. So we can see across 1, 2, 3, 4, 5, 6, 7 times that we missed capturing the 100. So that shows us down here, this 93% include the population mean because 7 of them missed it out of 100. We could keep drawing samples and watch more of these happen, and so everything is updating as we do this. We're seeing the sample numbers update and all the estimates update. And so that's how this table works. Again, there's help if you want more information in the documentation. Same thing for the population proportion. We name the population, we watch the sample and the sample summary statistics. We can watch the confidence interval being formed, and then we can watch whether or not they capture our true proportion. So let's say that our true proportion is 0.45. And we're going to look at heads. So we have a weighted coin, 45% chance of heads, 55% chance of tails. Let's take samples of size 20. And let's take 100 of them at a time. Let's animate this. And here we get the option to use the continuity correction. So if you want to do that, click yes. If you don't want to do that, click no. And draw additional samples will again show us all our samples, walk through each one, what the sample proportion of heads versus not heads is, and show us when we actually capture that 0.45, the true proportion. So out of 100, we missed 1, 2, 3, 4, 5, 6, 7, again, 7 times. So again, 93% contain this population proportion. Here, from our sample number 100, our sample proportion was 45%. It was 9 out of 20. Lower confidence interval, upper confidence interval for that confidence interval on the proportion, 23% to 67%. I can keep drawing more and more samples and see if this gets closer and closer to the 95% that I'm expecting. And I should find that as I take lots and lots of samples that I get closer and closer. We actually dropped slightly farther with this second 100, but the more I take, if I take thousands and thousands, I'll get closer and closer to the 95% confidence level. Again, there's help for more information about this applet. Okay, 2 more great applets here, the demonstrate regression and demonstrate ANOVA. Demonstrate regression allows you to choose from a normally distributed population or to create your own sample by sampling out of a data table. So let's look at that one first. So if I choose that big class data table I have open in the background, I could use weight as the response and height as the predictor and sample out of that data set. So this is just randomly choosing the X's and Y pairs to sample from those data. Population normal lets me choose. So if you remember when we chose my sample, this was a much simpler screen. It didn't have this population characteristics like this. When we choose population normal, then we choose what we want the intercept to be. So you can watch how the points move up and down for the intercept, or I could enter something here. I can choose what I want the slope to be. So what relationship do I want these points to have? Let's try to expand this axis so I can see the data. There we go. So if I do a -1 relationship, we can see that switch. How tight do I want the correlation to be? I can name this, so maybe my response is hours of sleep, and my predictor is number of exams that I'm studying for. So this would be a little bit crazy. The intercept is 5, and a negative relationship certainly doesn't make any sense. So I can change these to whatever I want. or I could just call these X and Y. The mean of X, I can rescale where these are located on these axes. So if I wanted this to be higher numbers, so let's say the mean of X is 10, and the standard deviation of X is 2, that's fine. We can also always revert to original, so that switched the direction back and put me back at the defaults. Then we want to look at the characteristics of the sample. So again, we have the sample size either with a slider or entering a number here. And how many samples do we want to take? Let's just take one to begin with. So here's our first sample. And one of the things I might want to do with this is to fit my own line to these data. So if I grab this little box, I can drag this around and try to fit where I believe the best fit line is. If I want to see this better, I can make this bigger by grabbing this bottom corner and expanding this. So that's where I think my best fit line is. I get to see my residuals on the side. So if I do a bad job of fitting the line, I can see how bad the residuals are. Same in this direction. So I can explore fitting my line and trying to get my residuals to be centered around that line. When I'm happy with my residuals, then I can say fit my residuals, and it shows me all those little lines perpendicular to the x-axis connecting to my line. So those are all my residuals, and now I can see show my squares. So now it squares those. For each line, the direction it goes up, it goes out the same amount. And then it shows me, if I added up the area of all those squares, here's the sum of squares from my residuals, from my errors. Now I can compare that to the true least squares fit line. So let's fit that least squares line, and I did pretty well this time. And then it shows me, and if I expand the scale, I can see better. I really got spot on with the red line. So I did a really good job of the sum of squares. My line was really close to the true. I can also show fitting the least squares residuals and the least squares squares on top of mine, but that's going to get really crowded. I can show the true line as well, because this was a sample. So this is the true population line that sample was drawn from. I can put just a fit mean line across to show if the slope was 0. This is what I should have gotten. I can put a normal quantile plot and a density ellipse on top of this. So here's the normal quantile plot. It shows up down here. I can look for the density ellipse. And I can save this sample to a data table if I want to. So it shows me all the XY pairs for this data set that it generated. So I could do more analysis with those data. So let's clear this and start over. So it's reopening the demo. If we used create your own, we could just specify the name of the response. So I want to call it Y. I want to call the predictor X. I can say I want Y to go from 40 to 50. And I want X to go from also from 40 to 50. So it gives me 2 points to begin with. If I click on one, I can drag it around. So I can make whatever shape I want to. So if you've ever wanted, and then I just click to add more points. If you've ever wanted to be able to create data sets just by drawing a picture and then seeing what those XY coordinates would be, this little tool of save sample to data table is really useful because I just clicked around all those X's and Y's and then it saved them out as points in this data table. So this is also a nice tool, not just for showing regression, but for creating your own sample data set. So I just built something that's curvy instead of a straight line. So when I try to fit my line to this, I'm going to have a hard time getting something that really works. Let's go back to population normal though, and I'm going to say restart demo. So here's another normal sample. Again, I can change where I want this to be the intercept and how much of a slope I want this to have. I can change the correlation of the points to more or less. I can change the names and so on. But this time, let's take a lot of samples. So let's take 100 samples this time. If I click Draw Additional Samples, now I can look at some summary information of all the samples. So now all the lines showed up, and I start seeing that all the lines kind of make what those confidence bands look like when I'm building a regression. Those confidence bands, the concept was that I could refit lots of different lines to lots of different samples, and hopefully I'm capturing that 95% of those lines are, that's what my 95% confidence interval is 95% of the lines I would create from different random samples. I can also see the average, the minimum, the max, the average standard deviation of those intercepts and slopes. So here the averages are pretty close to my actual intercept and slope, my true intercept and slope. I can look at more information on the individual fits from each line. And I can use this red triangle to look at more things. So I could look at the fitted lines. That's what I've got here. I could look at the intercepts instead. I could look at the slopes. So there's a distribution of the intercepts, the slopes. I can plot the intercepts by the slopes. I can look at the distribution of the correlations, the R-squares, the t-ratios for the intercept, the p-values for the intercept test, the t-ratios for the slope, and the p-values for the slope. So this distribution, that's interesting. We have one that's really surprising, and I think that that's probably going to match with this one really surprising line. So again, we can explore the actual least squares line, fitting our own line, and comparing to the true line, and so on. So there's more information here in the help. And now let's look at the demonstrate ANOVA applet. We have the means here, and we have group 1, 2, and 3 means if we have the 3 checked, or we can check 2 to just compare 2 groups. So let's make one of these maybe 20 as the mean, and the other as 30. So the grand mean, if these are equal sample sizes in both groups, is 25. We could change the standard deviation, make them really spread out, or make them really tight. We could change the names of X and Y here. We could change the sample size. So I could make this something bigger or something small. Let's draw one sample to begin with. I'm going to undisclose this distribution of test statistics. So let's draw this sample. So we see 2 F ratios to begin with. We see the minimum, the maximum, and so on. And we see the F critical value here for 1 numerator degree of freedom, 8 denominator degrees of freedom, 95% level, is 5.3177. If we look at the red triangle, we can look at the show rejection rate. And let's grab this axis. The rejection rate in this case is 1. So if I want to rescale this, I just grab the corners and drag down. So now let's draw a bunch of samples. So let's draw 99 more samples. So now when we see the distribution of F ratios, we see a lot. We see actually the F distribution starting to show up here. Again, let me pull this to the side so we can see the rejection rate. It's still 1. We had a very high power with a standard deviation of 2. We were pretty much always going to find this difference. So what if we look at instead something that's closer? So let's look at maybe 27 compared to 30. Now let's run 100 samples and see this distribution. So now our rejection rate is 0.67 something. We have again the F distribution forming from those F ratios, the same F critical value. So we can explore as we get things closer and closer together, or as we change the standard deviation. So even when they're close together, only 3 points apart, with a tiny standard deviation, high power; when they're more spread out, lower power. Okay, under the demonstrate ANOVA, we have the documentation. If you click on this, this will take you to the documentation of all of the applets. So lots of information on all of the applets. And if you click on the additional resources, then we have a few other options. Demonstrate p-value and power. These are built into the software when you're in the distribution platform. So here you can drag around the null value, the hypothesized mean, and you can see how that affects the t-ratio and the p-value when this fixed value is your estimated mean in the sample. So you can't change what you got from the sample, but you can change what test you were going to do. So you can see how that would have been different. You can switch to the high side or the low side or both sides. So same thing here. There's also the demonstrate power, which is also built into distribution, and a few other options. The permutation test for two means or two medians. This is going to use the data set that you have. So this is if you wanted to look at, for example, how heights of men and women differ. So I'd use height as my response. I'd use sex as my factor. I can resample this a bunch of times, and I can look at either the mean or the median. I could keep the original sample statistic somewhere in the table and click Run. And so here it's resampling the data for me. So these were the heights of females, heights of males, and the difference between them when it did these resamples. Here's the distribution of females, the distribution of males when it did the resamples, and here's a picture of the differences. So I'm clicking on these little green play buttons to repeat these analyses that got automatically put into that data table. So when I use this applet, these are automatically populated for me. So here I see this histogram of the differences between the resampled heights. So the height of men versus height of females centered around 0 from the resampled data. Because basically, if I just swapped who was male and who was female, I would expect that the difference on average between the people that get called females and the people that get called males, the difference on average will be 0. The true difference, however, if I show the original sample difference, is here. So it's kind of in the tail. And if I want to show the empirical p-value, let's show just the upper right-sided empirical p-value. So that one-sided p-value is 0.017, and the two-sided p-value is 0.028. So there's a lot of evidence that there truly is a significant difference in the heights, a statistically significant difference in the heights between men and women, because in this empirical distribution of the resampled data, so when we just permute, when we label swap, we see this distribution centered around 0, and what we actually got from our data, from our labels, the correct labels for men and women, is kind of extreme. If those labels meant nothing, if they could just be randomly reshuffled, then we found something really strange. Okay, so if you have any other questions on the applets, a lot of answers can be found in this applet documentation. Again, if you're using JMP Student Edition, there's an applets option right here in your menu bar. If you are using JMP the standard version or the pro version, then you would not have that applets option up here in the menu bar. You'd need to go to sample data from the help menu. So help, sample data, and then scroll down to this teaching resources section, go to the teaching scripts, the interactive teaching modules. That's the distribution calculator, distribution generator, those sampling distributions, confidence intervals, hypothesis tests, and demonstrate regression, and ANOVA. If you want to find more options like simulations and calculators and teaching demonstrations, there are other things hiding in this great tools place as well. And you can go to jmp.com/tools to find more teaching scripts and add-ins.